We talked about exponential functions. Yeah, it was yesterday. Um, and we talked about if you have, your different a values. A can't be 1. A has to be greater than 0. But if it's less than 1, it's exponential decay, which is what we see right here, this graph here. If it's greater than 1, we see exponential growth, which is the shape that we see for this graph here on the left here. So what I want to do today is to start off by taking an exponential function and us trying to graph it and see if we can figure out what it's going to look like and just get a basic graph of it. It doesn't have to be perfect or anything. If you want it to be perfect, we just use a computer, but we're going to see if we can figure out some information about this function by graphing. Okay. So first things first, do you think this is exponential growth or exponential decay? Growth. Why do we think it's exponential growth? Close. It is about the base. But what is the base here? 3. And it's not that it's positive, it's that it is greater than 1. Remember, if it's less than 1, it's going to be exponential decay. If it's greater than 1, it's going to be exponential growth. It shouldn't be equal to 1 because that would just be a constant function. And it shouldn't be negative because then we have that oscillation thing going on. So because 3 is greater than 1, this is going to be exponential growth, which means our graph is going to be shaped like that. And it's going to start off slow and then take off. Any questions on that? All right. So we'll start there. Let's start here. What is the domain of f? Negative infinity, positive infinity. Domain of all exponential functions in the basic form is going to be negative infinity to positive infinity. It is possible they throw an x in a denominator somewhere. You probably won't see anything like that in this class, but I mean, it is possible. In the realm of possibilities, it could happen. Or you could have a square root somewhere. Something like that. But for this class, it probably won't. What else we got? What is f of 0 going to be? 1. And so we know that our initial value is going to be 1. Remember, that's the c value in front of the base being raised to the exponent, which in this case is none. So that means it's 1. And what other information do we want to know? That's pretty good for right now. Let's find some other point stuff. We know that there's going to be 0, 1. Because we know that f of 0 is equal to 1. Excuse me. What's some other points you think we can do? You want to do x for 2? All right, we can do that. So if x is 2, y is going to be what? 9, because it's going to be 3 raised to the second power, which is 9. We can also do x is 1, which will give us 3. And we can go on. If we raise it to the third power, it should be 27. We know we get the 0, 1 already. What other point should we use? Negative 1 would work. So what is it going to be when we raise it to the negative 1 power? It's going to be a fraction, and a fraction is going to be what? 1 over 3, which is about 23. Just a bunch of repeating 3. And if we did negative 2, anybody know what that would be? Yep, 1 over 9, which is about, I don't know that. Yep, that makes sense. 0.11. You take 0.33 divided by 34. 0.11. And so with these points, we probably don't even need this many points, but we did our due diligence. We could probably graph our function using those. So we got 1, 3. So let's see how this is split up though. Actually, this is 10. So it looks like it's 2, 4, 6, 8. So each of these is 2. There's tick marks. So if we got 1, 3, that's going to be about here. No, that's not right. It's going to be halfway. 1, 3, it'll be about right there. We have 2, 9. That one's a little bit easier to do. That's going to be over here. 3, 27 is going to be, let's see, that's going to be 28. So it's below that. Right. So it grows pretty rapidly, you can see. And then we have -1, 33. Now we got to kind of figure out about where that's at. We got -2, 0.11. You know, it's about right there. I can only make it so low. And a 0, 1. It'll be about there. And so if we graph our function, it's just going to take off from there. Oh, I missed the point. Try it again. There we go. That's basically what our function looks like. So you can see this one grows pretty rapidly. I mean, they're all going to grow pretty rapidly unless there's some change happening. All right, so from there, what's our x-intercept? There's none, right? So there's none for x-intercept. What's the y-intercept? That's going to be our initial value for this one. That's going to be 0, 1. Or just y is equal to 1. Either way. And there's one last thing we talk about. This one. What's the range? Close. So this is getting closer and closer to what as we go along? It's 0.33, then 0.11, and it's going to be okay, closer and closer to 0. So what do you think the range is going to be? Yeah. From 0 to positive infinity, and we don't include the 0. Oh, I drew my purpose today. We don't include the 0. There's a horizontal asymptote happening there. So it keeps getting closer and closer to 0, but it's never actually equal to it. So the range is going to be from 0 to infinity, not including the 0. I think that's everything we can get from that. Any questions on that?
So is it the range ever will be from negative to evaluation, or just from
You mean, will it ever be that for any function or for an exponential function? No, I don't think it ever. It's always going to be some horizontal asymptote. It may shift it up and down. You know, it may be from -3 to infinity, or from 5 to infinity, depending on how it's shifted. But it's always going to be some horizontal asymptote happening. Now, well, we'll talk about that. Let me see, actually. Yes, we will talk about that in a little bit. But yeah, it's always going to have some starting spot, and it's going to go to either infinity or negative infinity, depending on what's going to happen. Any other questions on that? All right, so there are some things that we can learn about these and how they shift depending on what we do to the function. So we started out with the base function of f of x is equal to 3 raised to the x. And that is this graph right here. So one we just drew. Okay. What happens if we do 3 to the x minus 1? It's going to pull it down 1 unit. And so basically our graph is now going to be just shifted down 1 unit and like that. I didn't draw it perfectly, but I was trying to mimic it there. But just pull down 1 unit. Notice that initial value gets changed, right? Actually should hit on the origin there. Should be 0, 0 instead of 0, 1 because we're subtracting 1. So if you have that minus 1, it's going to shift it down. What if it was plus 1? It would go up 1 unit, and it would be, that's all right, up here. Okay. So that is what, we're going to go through all these rules later. I just want to show you examples of what is happening. But we'll look at some notes on what each one means. What we got here? What if our function was 3x, 3 raised to the x minus 1? So the minus 1 is now within the exponent. Yeah, it's going to be a tough one. Let's look at some values and see if we can figure it out. So what if x is 0? It's going to be what? 3 to the negative 1, which is going to be 1/3. What if x is 1? It'd be 3 to the 0, which is 1. What if it was 2? It's going to be 3 to the 1, which is 3. And 3 would be 3 squared, 9. So what is happening to it? So if you recall, it didn't flip it. You were almost right with the other one. You said it's going to shift it to the left. You're close. It's going to shift it to the right.
Oh.
You see, because instead of it there being at negative 1, 1/3, it's 0, 1/3. Instead of it being 1, 0, I'm sorry, instead of it being 1, 3, it's now 1, 1. Instead of it being 2, 9, it's 2, 3. So everything has been shifted to the right a little bit, and so, or 1 unit. And so your graph will be shifted over. I messed that one up once again. 1, 1. So as we already here. Oop. Then it's going to take off after that. That x minus 1 in the exponent, it's going to shift it to the right 1 unit. If it was plus 1, it would shift it to the left 1 unit. All right. There we go. What if it was 3 raised to the negative x? What's that? Yes. And why is that? The x is negative. So if I wanted to write this with the x being positive, it would be 1/3 raised to the x, which is a value that's less than 1. This is going to be exponential decay. Good. And we can do some values, see what it's going to be. If you put a 0, it's still going to be 1 there. We put a 1, it's going to be 1/3. 2 would be 1/9. If we put a negative 1, that's when it's going to be 3. -2 would be 9. -3 would be 27. So it's kind of flipped around. So instead of it doing this climb, it's going to fall. Go like that. It's going to fall real fast and then slow down. So it kind of like flips this on the vertical axis, kind of flips it around. Any questions on that? And then the last one, which I think this is the hardest one. Well, actually, I feel like the 3 raised to the x minus 1, that one always confuses me a little bit because it's the opposite of what I would think. What if it was f of x equal to negative 3 raised to x? So notice that negative is not part of the base. It's tacked on in front. Yeah, anybody have a guess of what's going to happen there? Don't feel bad if you don't, because this is tough. We'll throw some points out and see what it's going to be, but anybody have a guess? Huh? All right, well, let's see. Let's do some points and see if we can figure it out. So let's do x, let's do y. Let's start with 0. So if we raise it, if we negative 3 raised to the 0, it's going to be what? The 3 raised to the 0 is going to be 1, and we're going to negate it. So it's going to be negative 1. Right? If I do a 1, y is going to be negative 3. Do a 2, negative 9. Do a 3, negative 27. What do you mean by that?
I don't know, it just made all our values negative.
Mm-hmm. So instead of it climbing like that, what is it going to do? It's going to dive. So our function is going to do this. It just dive down. So basically, it's like exponential growth, but it just flips it over. It's just diving real fast. It's exponential growth in the opposite direction.
But why wouldn't that be decay? Because it's
So decay is more like it decays quickly and then it slows down. So you see how that's a totally different thing. It's slowly decreasing and all of a sudden it just dies. Oh, my marker stopped working again. I have to refresh the page. Give me one second. Didn't I restart? No, I didn't restart my computer. I usually try to restart it every day so that doesn't happen. There we go. So decay is it starts up here and it drops quickly and then it slows down. This is exponential growth just flipped. So it's slowly decreasing and then it just decreases rapid. So it's a little bit different. So this would be exponential decay. But the blue one is not what we call exponential decay. I don't know if there's a name for it. Yeah, I've never heard of it. I mean, it's an exponential growth just function just flipped. Any other questions on that? So let's take a look at what we've figured out from that. I got some notes here. I don't know where I took this from. I think I took it from a website. So these are some general notes, the shifts of the function of the exponential function. Notice they write theirs as f of x is equal to b to the x. So instead of a, they use a b. So what you can have are all these different things that are happening. You have f of x is equal to b to the x plus c, and then that plus d. Okay? And so we're going to talk about what that will do to the base function. They call it the parent function of the exponential function. So the d is going to shift it vertically, and it's going to be the same direction as the sign of d. So if d is positive, it's going to shift it up so many d units. If d is negative, it's going to shift it down d units. The c, that's the number being added to the x in the exponent. It's going to shift our function horizontally, so to the left or to the right, and it's going to be in the opposite direction of the sign. So if it was minus c, it's going to shift it to the right c units. If it's plus c, it's going to shift it to the left c units. And here's some other stuff. Remember we talked about the y-intercept before is always 0 and the initial value. Well, that can change if you have that plus d. So we're going to make it, and the c actually will change too. So it's always going to be 0, comma, b to the c plus d. That's going to always be your y-intercept for all the exponential functions without making any generalizations.
Wow.
Mm-hmm.
So for C, it says polynomial C on it. So
Yep.
if it's a positive, it's going to move left, and if it's negative, it's going to move right.
So if it's plus c, yeah, it's going to move left. If it's minus c, it's going to move right. Yes. Yeah. I had to think about that. It gets me every time. The horizontal asymptote, remember I said that could shift? It's always going to be y equals d. Whatever that d is, which in our basic function is 0, so it's 0 most of the time, but it's always going to be whatever d is. That means the range is always going to be from d to infinity. Now, one caveat to that. If the function is like that last one we looked at where it was negative e to the x plus d, the range won't be from d to infinity because remember it fell drastically down. So it's going to be from negative infinity to d. So if it's got that negative in front of the exponential part, that's going to switch the range up. Okay. So that's one of the ones that aren't listed in this note. But one thing that's nice, domain, we can always count on it for exponential functions. That domain can always be negative infinity and positive. We can put whatever we want in the exponent. It's totally okay. We can put pi in the exponent, but whatever. Doesn't matter. Any questions on that? All right, I think that's all I got on this. I think I added this one, so blank check. All right, so let's talk about E. Anybody ever heard of the number E before? No? Okay. So E is called, or is named, Euler's number. That's pronounced Oilers. It's kind of like the old football team, but I think y'all probably don't remember the word. That's how it's pronounced. Not Euler. There's some debate on who discovered it because people discovered it at different times and to different levels, but I usually go with this one. It's discovered by Jacob Bernoulli while studying compound interest. Basically, the thing was, if you know anything about interest, like your normal bank account compounds interest once a month. Right? Every month they recalculate the percent of interest amount that you get and they add it to your account. That's what's compounding. And they do it again with a new balance the next month. And it just keeps building and building and building. And he wanted to know, as an economist, basically, all right, well, what if we compound it once a week? What if we compound it once a day? What if we compound it once an hour, a minute, a second? What if we just constantly compound the interest? And when he did that, he ended up finding what E was. And so this is what he did. This is the formula that you use for compounding interest. And whenever you make n extremely large, that's how often it compounds. This is the number you get, and that is relative. That's basically what E is. If you want to know what it exactly is, you can do it on your calculator. E is equal to 2.7. That was a bad 7. Let me hold it. 71828 18. Hmm? Oh. So on your calculator, there's either it's going to be E to the X button, or you may just have E, or you may have E with a caret. If it puts a caret for you to raise it to a power, just put 1 and then hit enter, and it will give you what it is. And there's some reason why E is an extraordinary number that we give it its own name and such. Um, but it's kind of out of the realm of this class, in my opinion, of what makes it um, kind of amazing. But you can look it up on your own if you're interested in it. If you go on in your studies, you'll probably learn more about it. But as far as we know, or as far as we'll go with this class, just assume it's a number similar to pi, right? The symbol we use to talk about a single number, just so that we don't have to write 2.718281828 every time we want to write it. And that goes on and on. I want to put 3 dots and I only put 1. So that's basically all it is. There's something else I was going to say about it. I totally forgot what it was. Oh, it is used very often in modeling things. So, like I was talking about the population models, the carbon dating models, a lot of those use E. Now, it's going to be E to different exponents and stuff like that going on, but E is used in a lot of those different models in everyday or in the real world. So, what does the graph of E to the X look like? Basically, this. So you have the point 1 comma E, of course you have the point 2 E squared, and we're gonna have that 0 comma 1, that initial value. And so it's just an exponential growth function because E is greater than 1, so it's gonna be exponential growth. And that's just what the graph of it looks like. It's nothing special, it's just, it is a special number, but the graph looks just like any other exponential function, really. All right, any questions on that? So we're going to work some problems that have E in it, but we're just going to treat it as any old base. It's just the base of E. Okay. So let's talk about solving exponential equations. This is kind of what I was leading up to this whole time. We want to talk about exponential functions and what it can be used for, but the main thing I was trying to focus on is getting to this, solve exponential equations. So it's difficult for us to solve exponential equations if you haven't done it before, because it's just like, how do I get the variable out of the exponent? And the way that we're going to look at is that if you have base A raised to the U, and that same base A raised to the V, and they are equal to each other, because of that, we can assume that the U has to also equal V. So, if you are given 3 squared is equal to 3 to the X, it'd be 2 and X equal. Why? Because the only way to make 3 squared equal 3 to the X is for this number and this number to be the same. So you know from there that X is equal to 2. Any questions on that? What if they started you out like this? 9 is equal to 3 to the X. What can you do?
But I know what to do, but I don't know.
You can see it maybe what's the word I'm looking for? Instinctively, right?
Yeah.
But we can also rewrite this as 3 squared is equal to 3 to the X, right? And now since we have the base are equal, 2 is equal X once again. What if we had, do I have room here? Yeah, I got room. What if we had don't want to go that far. Now let's keep it simple. What if we had 4 squared is equal to 8x, 8 raised to x? What do you think we can do there? Do they have the same base now? Can I express 4 base 8 as like 8 to some power? No. Can I express 8 as 4 to some power? No. 4 to 1 is 4. 4 squared is 16. It skips right over 8. Is there a base I can represent both of those in that's different than what they are now? Yeah, you could do that if you want. You could make the left-hand side 16, but it's still not going to get you anywhere, right? Because you can't represent 16 as 8 to some power. What's a base we could represent 4 and 8 in? The same base.
64?
I'm thinking the opposite direction. You can get to 64 from both of those, right? But if I wanted to write them in the same base, I want this to be the same number as this. 2. Yeah, 2 is right. I can represent 4 is 2 squared, right? So this would be 2 squared to the second power. 8 is 2 to the third. So it's 2 to the third raised to x. Good, Shayla. And so now I'm almost there. What do I do with these exponents here? Anybody remember?
Yeah.
Close. You multiply. So it's going to be 2 raised to the 4th is equal to 2 raised to the 3x. And now, since I have the same bases, I have a base 2 on both sides. That means their exponents have to equal each other. So 4 has to equal 3x, which if I solve for x is going to equal 4/3. That is probably the most advanced kind of one you'll see. A bunch of examples. Any questions on that? All right, let's try some other ones. So here I got 5 squared is equal to 5x plus 1. What are we going to do there? Yep. Yes. So since it's already the same base, it's 5 and 5 on both sides. You can set their exponents equal to each other. So this is going to be 2 is equal to x plus 1, which means x is going to equal 1. Any questions on that? All right. Well, let's do A together, and then I'll let y'all do. They're both A. Let's do the first one together, and I'll let you do the second one by yourself. That one's similar to the other one we did. So we got 3 raised to the x plus 1 is equal to 81. What are we going to do there? I'll give you a hint. Usually you look at the smaller base and go, hey, can I write that larger number in that base? Can I write 81 as 3 raised to some power?
Yeah.
3 raised to the 4th power. If you have trouble doing that, I'll just give you a little help here. Just divide it by 3. What do you get? You get 27. Divide that by 3. What do you get? You get 9. Divide that by 3. You get 3. 3. How many 3s I got? 1, 2, 3, 4. So or you just do it in calculator. So we're gonna 3 to the x plus 1, 2 to the 3 plus 1. And so now since we have the same base, we know that those exponents need to equal each other. X plus 1 is equal to 4. And so x will equal 3. You can always plug it back in, check to make sure that it works out. Any questions on that one? All right, well, y'all try the second one. And then before, we want to get these to have the same base. They do not right now. We can't represent 8 in base 4, so we're going to have to choose kind of like a common base for them to work with, a common ground. And so both 4 and 8 can be represented as 2 to some power. So we're going to have 2 squared raised to the 2x minus 1. You go to 2 to the third raised to the x plus 3. Any questions on getting there? This next step is where everybody seems to mess up. So what do we do with those exponents? What do I do with the 2 and the 2x minus 1? We're going to multiply them. So that means that 2 is going to distribute. When I go to the 2x, it's also going to go to the minus 1. So this is going to be 2 raised to the 4x minus 2. On the right-hand side, the 3 is going to distribute as well. It's going to go to the x. Also, you're going to go to the 3. So this, on the right-hand side, is going to be 2 raised to the 3x plus 9. And so now, since we have base 2, they're equal to each other. We know their exponents are equal to each other at this point. So we're going to have 4x minus 2 is equal to 3x plus 9. And we need to solve that. So let's subtract 3x from both sides. We'll get x minus 2 is equal to 9. Add 2 to both sides. And I get x is equal to 11. Yep. Any questions on that? No? Good? All right, so one thing I would like to ask is this problem here. Is this the same problem as this one? So, well, think about it. All right, this is 3 to the 1 times 3 to the x is equal to 81. What do you do with those exponents when you multiply those? You're going to add them. So what does that left-hand side equal? E to the x plus 1. So that is an equivalent equation. So if you do see something like that, what you want to do is get it into the form where there's a single base on each side. You don't want to start here because we don't have a single base raised to some power to work with on the other side. So that's one of the things. I didn't see any examples like that other than one that we do later, which seemed like a giant step. So that's why I want to do one like that here. The other one, the 4 to the 2x minus 1, that could have been written as 4 to the 2x over 4. Because remember, when you divide, what do you do with their exponents? You subtract them. So this is the same thing as 4 to the 2x minus 1. The other side could be represented as 8 to the x times 8 to the third. Because that would end up giving us 8 to the x plus 3. So that's just some different things you can see. Oh, really, like I said, the examples that start with E, and I wanted to introduce you to them before we get to those. Any questions on that? What else I got? I think these are kind of elementary. Yeah. Well, we got time. I feel like the other ones we just did was more difficult. Oh, sorry. Computer's lagging a bit. There we go. Give those two a shot. And we got 36 is equal to 6 raised to the 5x. What's the base that we're going to choose to use? 6. And so on the left-hand side, it's going to be 6 squared is equal to 6 raised to the 5x on the right-hand side. And so since we have the same bases here, single base on each side, we know those exponents are going to equal each other. So 2 is going to equal 5x. We divide by 5. And so x is going to equal x. Any questions on that one? All right, in the second one, you look at 243, you can't express that in base 9. It almost does, but you end up with, like, I think 9 times 9 times 3. Is that right? Yes, that is right. And so you can't express that one in base 9. And so, well, what base did we choose then? 3. So we're going to go with base 3. So on the left-hand side, it's going to be 3 squared raised to the 3x plus 1. On the right-hand side, it's going to be 3 to the 5th. And so we're going to distribute that 2. It's going to go to the 3x. It's going to go to 1. That's what I messed up on. So this is going to be 3 raised to the 6x plus 2 is equal to 3 to the 5th. Now we have a single base on each side. They're the same base. We can set their exponents equal to each other now. We can say 6x plus 2 has to equal 5 for that to be true. And we'll subtract 2. We'll get 6x equal to 3 divided by 6. And x is going to equal 1/2. Any questions on that one? Nope. Let's see what else I got prepped. I got some other problems in my notes that I kind of like. Yeah, let's we are going to do that. Let's do that later. What else I got here? Okay, that's just a blank page for me. That's not what I want. There. All right. What if you got, let's just call this number 1. What if you got this? There's actually a few ways to work this one out, but think about it. We got 1 over 5 raised to the x is equal to 1 over 125. What do y'all think we can do? Okay. All right, so you're saying you're doing this. 1 over 5 to the x is equal to 1 over 5 to the 3rd. Okay, but does that set up the way that we talked about before? It's a little different, right? They're both in the denominator of a fraction. If the numerators weren't the same, then we couldn't assume they're equal. Another way to think about it is, remember if you have a fraction with the numerator 1 and the denominator is raised to a power, you can rewrite that like this, right? Because the x applied to the 1 is just going to be 1 anyways. And on the other side, we can make it 1 to the 5th, 1 over 5 raised to the 3rd. Because the 3 applies to 1, it's just going to make it 1 anyways. In all honesty, you can really, once you're at this point, assume that this exponent is equal to this exponent. But if you want to be more mathematically sound, I would go with this. And so now we can assume x is equal to 3, and we're done at that point. We don't have anything else to solve. Any questions on that one? What if it was, what's one that I know? Something I don't know any. 1 over 7, x is equal to, is that right now? 1 over 7 raised to the x is equal to 343. First question we gotta ask, so what base are we gonna use? 7. We can represent 343 as 7 to the what? 3rd power, yep. And so can we make that 1 over 7 to the x 7 to some power? How can we bring that into the numerator?
The 7 make the x negative.
Yeah, so we can write that as 7 raised to the negative x. And now we have the same base on both sides. That means the exponents are equal to each other. So negative x is equal to 3, which would mean that x is equal to negative 3. Any questions on that? Some people struggle with it if it's do an example like that. Now, these don't necessarily just have to have one solution, which I'll show you here. So what if we have 3 raised to the x squared minus 7 is equal to 27 raised to the 2x. And hopefully these numbers work out. I have it written down. So should be a good problem. So when I look at this one and I see that x squared in the exponent, it makes me think, oh, I may end up with a quadratic equation in the end, which may end up giving me 2 solutions. No solution or 1 solution, but it's possible it could be 2 solutions. So that's one thing we gotta look out for. So got a base 3 here. Can I represent 27 at base 3? Yes, I can. So this would be 3 raised to the x squared minus 7 equal 3 to the 3rd raised to the 2x. And so let's rewrite it now. It's going to be 3 raised to the x squared minus 7. On the right-hand side, let's multiply that 3 into 2x. So we have 3 raised to the 6x. Now we have single base, same base on both sides. That means the exponents are equal to each other. And so what we end up with is a quadratic equation of x squared minus 7 is equal to 6x. And we're just going to solve it like any other quadratic. We want to get one side equal to 0. So I'm going to subtract 6x from both sides. I have x squared minus 6x minus 7 go to 0. We could try to factor it. It looks like you can factor it. Negative 7, positive 1. Yeah. So this could be x plus 1 times x minus 7. If it didn't factor, we could use the quadratic formula. I mean, you can use the quadratic formula here even if you wanted to. I mean, if you wanted to, you could use it here too. And so this is going to give us x is equal to -1 and positive 7. So we're going to have two solutions for that exponential equation. Those are always interesting because it's weird to think that you can. I guess it won't be raised to a different power per se. The square is going to change. That's why. That's what's going to happen. Any questions on that? All right. So let's talk about what if the base is equal. So I don't know what number I'm on at this point. I feel like it's 4. I feel like it's 4. If we have e to the x is equal to e raised to the 3x plus 8. Same concept as we did before, just the base here is e. But we have the same base already. Our base e on the left-hand side, and base e on the right-hand side. There's a single base raised to a power. So that means that their exponents are equal to each other. That means that x is equal to 3x plus 8. And then we just need to solve for x. So we'll subtract 3x. Yeah, that'll give us what? -2x is equal to 8. Divide by the -2, and x will equal -4. So the e really doesn't play much of a role here. It's just a base, and then we end up getting rid of that base. Once we get a single base equal to the other on both sides. Any questions on that? One last one. It's a tough one. There's another example of this one in the book. I mean, the notes, and probably the book too. But I wanted to change it up a little bit. So e raised to the x squared is equal to e raised to the 3x over e squared. Close. You're talking about this, and this?
Yeah.
The problem is that this is 3x. If it was just 3, then yes, it would be e to the 1. But 3x and the 2, those aren't like terms, so I can't do the actual subtraction. But you are right that our next step would be that it would be e to the x squared is equal to e to the 3x minus 2. But I can't do that actual subtraction. And so at this point, I have base e on the left side raised to a power, base e on the right side raised to a power. That means those two powers are equal to each other. So x squared is going to equal 3x minus 2. And once again, we end up with a quadratic equation. Let's get one side equal to 0. I'm going to move the 3x and the 2. I like to keep that a term positive. But either way you want to do it, you should get the same answer. So I'm going to have x squared minus 3x plus 2 is equal to 0. That one does not appear to factor. Oh, yeah, it does. Yeah, so we can do x minus 2, x minus 1 is equal to 0. I didn't catch the sign. Good. And so we're going to get two solutions from that, right? We're going to get x is equal to 2 equal to 1. I was wondering why I made one of the answers quadratic form. Any questions on that? Like I said, there's another example of one like that in the notes if you want to check it out. I just didn't like it because it had a negative on one of the exponents. I'd rather not confuse you by working with that in it, but you can always check it out on notes.